Illustrate how confidence intervals work, let's start with the population of NBA Heights from the 2014 season, which you may remember had a mean of 79 inches with a standard deviation of 3.5 inches. And then let's think about a sampling distribution of means from this population for samples of 4 players. Notice that the x-axis here is marked off in increments of 1.75, which is one standard error for a sampling distribution with n equals 4. Now suppose we were going to use this sampling distribution to conduct a two-tailed z-test with alpha of 0.05. The critical values are negative 1.96 and positive 1.96, marked here just inside the range of negative 2 and positive 2 standard errors. If we were using this as the null distribution for a hypothesis test, values that we obtained outside this range would be considered statistically significant, and we would reject the null hypothesis that the observed value was consistent with this sampling distribution. The range between the critical values consists of all the values that would not be considered statistically significant deviations from the population mean. Again, with alpha at 0.05, the interval is 1.96 standard errors in either direction, almost 4 standard errors in total. Now let's take some random values from this distribution, shown at the top of the screen. Each dot represents the mean for one random sample with n equals 4. Of these 25 random samples, 1 falls outside the bounds of the critical values, which is about what we would expect with alpha of 0.05. If we were conducting a two-tailed z-test and obtained a sample with this value, our decision rule would lead us to call this result statistically significant, but that would be a type 1 error because this value actually did come from this sampling distribution. All of the other means fall in the range between the two critical values, so they would not lead to rejection of the null hypothesis in a z-test. Let's spread these values out, and for reference, we will extend the line for the mean of the sampling distribution. Now, notice that if we take an interval the same width as the interval between the critical values, and center that interval around each of our randomly selected means, all of these intervals except the one that goes with the type 1 error will include the population mean. This is the critical point. If we take an interval as wide as the distance between the critical values and center that same interval around each of the randomly sampled values, in the long run, a proportion of the intervals equal to 1 minus alpha will include the population mean. With alpha at 0.05, as is most typical, this means that 95% of the intervals around randomly selected sample means will include the population mean, as you can see here. An interval drawn around a sample mean in this way is called a 95% confidence interval because we can be 95% confident that if we repeat this procedure many times over the long term, 95% of the intervals will include the population mean. Of course, this is an unusual example because we happen to know the population mean in this case. In the more typical situation, the reason we take a sample in the first place is to get an estimate of the mean because we do not know what it is. And because research is time-consuming and expensive, we typically only draw one sample of the largest size that is practical. So we could draw one sample of people and calculate the mean height to get a point estimate of the mean height of whatever population those people come from. And then we can construct a confidence interval knowing that in the long run, 95% of those intervals will contain the mean of the population from which this group of people was sampled. In this more typical situation, a confidence interval is useful because it conveys information about variability and about the size of the sample that the mean alone does not. For a z-test with alpha at 0.05, each half of the confidence interval, the part below the point estimate and the part above it, is about 2 standard errors. Recall that the standard error is a function of the standard deviation and the size of the sample. So when a variable has less variability, that is, when sigma is smaller, the 95% confidence interval will be smaller. And that makes sense. When there is less variability in the data, the sample mean will tend to be closer to the population mean. Also, when larger samples are drawn, that is, as n gets larger, the confidence interval will become smaller. Again, this makes sense because we know that we get more accurate estimates of the population mean when we draw larger samples. Remember that another thing that confidence intervals communicate is statistical significance. Any value that falls outside the confidence interval is statistically significant. Suppose we take samples from several populations that we think might have mean heights different from the mean for the NBA. We can plot these point estimates along with a line marking the mean height for the NBA, and then we can put confidence intervals around the sample means. Notice that some of the intervals include the value of 79 inches, but others do not. These means with confidence intervals that do not include 79 inches are statistically significant. Also notice that some of the intervals are smaller than others. All of them are based on the same population standard deviation, but we generated some of these intervals with different sample sizes. The larger the interval, the smaller the sample size. To summarize, confidence intervals are useful because they instantaneously convey information about the sample mean, variability and sample size, and statistical significance.